In today's video lecture, we are going to begin the packet of notes dealing with second-order RLC circuits. This is covered in the book in Chapter 8, specifically sections 8.1 through 8.4. Today is going to be a lot of theory, a lot of background material, a lot of Math 250 review, and then we're going to break down RLC circuits into two specific types, source-free and driven. And just like in the first order case, source-free circuits are ones where there is no source present after some time t0, and driven circuits are ones where there is a source present after some time t0. We're going to see that the second order RLC circuits are very similar to the first order RC and RL circuits, except that the math does get a little more intense. So let's get straight to it. Okay, so first off, what makes up a second-order transient RLC circuit? Well, the first thing you need is both an inductor and a capacitor. So a big difference from the first-order case. Then, just like the first-order case, you need a change in the circuit at time t0. You need to either change the value of a voltage source, add a voltage source, remove a voltage source, add a resistor, remove a resistor, something to change the circuit at time t0. The final thing you need is one or more resistors. The reason you need the resistors is the resistors are going to dissipate whatever energy is stored in the capacitor and inductor. If you do have a circuit that has only a capacitor and an inductor and no resistor, we call that a lossless LC circuit, and we're going to see that that is an oscillator. We will look at this as a special case of RLC circuits. What we're going to see in these RLC circuits is that we end up with a second-order differential equation to model the system. One point that I should make is with this requirement that you need an inductor and a capacitor. Well, it turns out that in some cases you could have, for example, two different capacitors. Maybe a circuit like this, where the capacitors cannot be combined into a single equivalent capacitance. This is also second order. On the other hand, if you had a circuit like this, where the two capacitors could be combined into a single capacitor, this actually reduces to a first order. Anyway, in this packet of notes and in this course, we will not look at circuits like this that have two capacitors or two inductors that cannot be combined. We're only going to look at cases where you have one capacitor and one inductor. To sort of see where these differential equations come from, let's look at the two cases. First off, a series RLC circuit, and then we'll look at a parallel RLC circuit. So let's assume we have a series RLC circuit where you have initial energy stored in the capacitor and the inductor in the form of current through the inductor, which stores energy in the magnetic field, and the voltage across the capacitor, which stores energy in the electric field. Let's add some variables to this very simple circuit. If IL is defined as the current going through that inductor going up from the passive sign convention, VL is defined as that. Let's define IR as the current going through the resistor from left to right, so VR has that orientation from the passive sign convention. If VC is the voltage across the capacitor with the plus sign on top, then IC is that current there. Note that the way I define these variables, IL equals IR equals IC, they're all going in the same direction. Let's do KVL analysis to see if we can come up with our equations. Starting at this point here, Let's sum voltage drop plus voltage drop plus voltage drop equals 0 and see what we get. We get VL plus VR plus VC is equal to 0. The voltage across the inductor can be written as L times the derivative of the current through the inductor. The voltage across the resistor, of course, is R times the current through the resistor. And the voltage across the capacitor is 1 over C times the integral of the current through the capacitor. Now, because IL equals IR equals IC, we could rewrite this as L times DIL dt plus R times IL plus 1 over C times the integral of IL d tau is equal to 0. Let's take the derivative of every term in this equation and divide by this leading coefficient L. We end up getting that the second derivative of IL plus R over L times the first derivative of IL plus 1 over LC times IL is equal to 0. And we see that we have a second order constant coefficient differential equation of the form x double prime plus ax prime plus bx is equal to 0. Alternately, we can look at it this way. We start off with the same KVL equation, VR plus VL plus VC is equal to 0. And VL is L DAL dt. VR is still R times IR. Let's leave VC as it is. But what do we know about IL and IR? IL equals IR equals IC, and IC is equal to C dVC dt. So we can plug this into here and into here to get the following. You get LC times the second derivative of VC plus RC times the first derivative of VC plus VC is equal to 0. Finally, we can divide every term by LC to get the second derivative of VC plus R over L times the first derivative of VC plus 1 over LC times VC is equal to 0. What we see here is that whether we're talking about the current through the inductor or the voltage across the capacitor, in both cases we get a differential equation of the form of x double prime plus ax prime plus bx is equal to 0. Even though we're talking about two different variables here, IL and VC, notice the coefficients are the same. 1 R over L and 1 over LC. Let's look at a similar situation with a parallel combination of resistor, inductor, and capacitor. Once again, we have some initial stored energy in the form of these initial conditions. And once again, IL is defined as the current going through the inductor going down. And so using passive sign convention, VL is that. IR we will define as a current going through the resistor from top to bottom. So VR is that. VC is given for us. It's the voltage across the capacitor with the plus sign on top. So once again, from the passive sign convention, IC is that current going down. Notice that VL, VR, and VC all have the same orientation. To try to come up with the differential equation for this circuit, let's do KCL at this top node. Basically, that current plus that current plus that current has to equal 0. So we have, starting from the right, IC plus IR plus IL has to equal 0. But from the VI characteristics of the capacitor, we can write the current through the capacitor as C times the derivative of its voltage. From Ohm's law, we could write the current through a resistor as the voltage across the resistance over its resistance. From the VI characteristics of an inductor, we can write its current as 1 over L times the integral of its voltage. But from over here, we know that VL, VR, and VC are all the same, so we can replace VR and VL in this equation here with VC to get C dVC dt plus VC over R plus 1 over L times the integral of VC d tau is equal to 0. Let's now take the derivative of every term in this equation and divide everything by this leading coefficient C. If we do both of those, we end up with the second derivative of VC plus 1 over RC times the first derivative of VC plus 1 over LC times VC has to be 0. Note, once again, this is a differential equation of the form x double prime plus ax prime plus bx is equal to 0. Suppose we're interested not in VC, but in coming up with the differential equation for IL. We can start off with the same first step. Rewrite IC as C dVC dt. IR is VR over R. IL we'll leave alone at this point. But what do we know about VR and VC? VR and VC both equal VL, and the voltage across an inductor is DIL dt. So we can now plug that into there and that into there to get CL times the second derivative of IL plus L over R times the first derivative of IL plus IL is equal to 0. If we then divide everything by CL, we get the second derivative of IL plus 1 over RC times the first derivative of IL plus 1 over LC times IL is equal to 0. As we saw on the previous page, we get a differential equation either in VC or IL that are both of the same form. X double prime plus AX prime plus BX is equal to 0. And notice these have the same leading coefficient. This term has the same leading coefficient. And this term has the same leading coefficient. So let's look at this differential equation in more detail. What we see is whether we have a series or parallel RLC circuit, we end up with a homogeneous second-order differential equation of the form x double prime plus ax prime plus bx is equal to 0. This term A is either going to be R over L in the series case or 1 over RC in the parallel case. B, whether we're talking about the series or the parallel case, is always 1 over LC. And X is either IL or VC. So let's think about the solution of this homogeneous second-order differential equation. What this equation is telling us is that there's some function x that if you take that function, take its first derivative, and take its second derivative, and add them all up with certain coefficients, you can get 0. So then the question is, for what function are the derivative and the second derivative both of the same form as the function itself? And the answer there is the exponential. And so what we need to do is determine what this coefficient a is and what this value s is going to be. So how do we determine a and s? The way we determine s is similar to what we did in the first order case. We assume a solution of the form a e to the st. The first derivative then is sa e to the st. The second derivative is then s squared a e to the st. We're now going to plug this in here. We're going to plug that in here and plug that in here. And we end up getting s squared a e to the st plus as a e to the st plus ba e to the st is equal to 0, which of course you could then simplify as s squared plus as plus b, all of that times e to the st is equal to 0. For this to always equal to 0, what we have is that this part in brackets must equal 0. This gives us the characteristic polynomial, which you probably remember from Math 250. S squared plus as plus b is equal to 0. So how do you solve for s's then? We use a quadratic formula. If you recall, if you have a quadratic of the form as squared plus bs plus c is equal to 0, the roots are what? Minus b plus or minus the square root of b squared minus 4ac, all of that over 2a. We have a slightly different situation here because our variables, our coefficients, are slightly different. We're looking at s squared plus as plus b is equal to 0. So in the equations we have, what we're calling a is b in this more traditional quadratic. What we're calling b is c in the more traditional quadratic. And what the more traditional quadratic calls a, we just have as 1. So the two roots then are s1 and s2 equal minus a plus or minus a squared minus 4b over 2. Once again, this is the same as this expression here. If you replace a with 1, if you replace b with a, and replace c with b. They're just variables, so you can call them whatever you want anyway. Anyway, a couple important points. We saw that a viable solution is going to be a e to the st. Since there are two values for s, there's going to be a linear combination of two exponentials that can satisfy this differential equation. So we're going to say that a solution to this differential equation is going to be x of t is a1 e to the s1t plus a2 e to the s2t, where once again s1 and s2 are the two roots. Second thing we see is that we're going to have three different flavors for this general solution, depending upon whether the radicand, and the radicand is the part inside or underneath the radical. If the radicand is positive, in other words, if a squared is greater than 4b, you will get real and distinct roots. We're going to call that the overdamped case. If the radicand is negative, you're going to get complex conjugate roots because the number inside the radical is going to be a negative number. We're going to call that the underdamped case. Finally, if a squared equals 4b, we get two identical roots, and we call this the critically damped case. So that is how we find S. How do we find the two scale factors A1 and A2, these two values here? They're going to come from the two initial conditions. Remember, we know that VC of T naught is some initial condition, and we know that IL at T naught is some initial condition. We'll get to that later, though. Continuing on with the solution, we see that we have three different cases. Let's evaluate them mathematically. First case is the overdamped case. It's the easiest of the three cases. This happens when a squared is greater than 4b. So you're going to get two real roots, minus a plus the square root of a squared minus 4b all over 2, and minus a minus the square root of a squared minus 4b all over 2. An important point is that if b is greater than 0, S1 and S2 will always have the same sign. This is always going to be the case in 210 because what is b? B is 1 over LC. 1 over LC is always positive, so B is always positive. So when you have the overdamped case, you're always going to have S1 and S2 will have the same sign. Not only that, not only are they the same sign, but also they're both negative, in 210 at least. You could certainly have differential equations where the roots of the characteristic polynomial are positive. In E210, however, they're always going to be negative when you have an overdamped solution. So continuing on, we're going to see that our solution in this overdamped case is going to be some coefficient a1 e to the s1t plus a2 e to the s2t. For example, you might have something like 5 e to the minus 4t plus 6 e to the minus 2t. Or maybe you have minus 7 e to the minus 2t plus 8 e to the minus 8t. Or you might have minus 6 e to the minus 3t minus 18 e to the minus 4t. But notice in all cases, these numbers are going to be negative. So what is the shape of this overdamped solution going to look like? Let's assume we have a characteristic equation, s squared plus 2s plus 0.5 is equal to 0. In other words, a is 2 and b is 0.5. When you plug those into the quadratic formula, you get negative 0.29289 and negative 1.7071. If you were to plot e to the minus 0.29289t, it might look something like that. If you were to plot e to the minus 1.7071t, it might look something like that. Notice that as the magnitude of s goes up, we get a faster decay. So the one that has a larger s has a quicker decay. The one that has a smaller s has a slower decay. In other words, you can sort of think that s is sort of like 1 over a time constant. Since your total solution is a linear combination of something like this and this, the actual shape can take one of two forms. For example, if x of t was 1 e to the s1t plus 1/2 e to the s2t, if you add those together, you might get a decay that looks like that. On the other hand, suppose the coefficients a1 and a2 were 1 and negative 1/2. You work out the math here, you would see that the response actually goes up a little bit before going down. So bottom line, when you have an overdamped solution, the response is either going to look like a decay, or it's going to look like a decay with a little hump in it first. And it depends on A1 and A2. All right, let's look at the more complicated cases now. Case 2 is where the radicand is negative when a squared is less than 4b. This is where the math gets a little tricky. So applying the quadratic formula, the two roots are still minus a plus or minus the square root of a squared minus 4b over 2, which a squared minus 4b is negative, so we can rewrite that as negative 1 times 4b minus a squared, where 4b minus a squared is now greater than 0. The square root of negative 1 is I. Actually, for the rest of your life now, the square root of negative 1 is going to be j. Although mathematicians use the letter I for the imaginary number, in engineering we use the letter j. The reason being is very simple. We are already using the letter I for current. And you may ask, well, why do we use the letter I for current, not the letter C? Because we're already using the letter C for capacitance. We sort of run out of letters. But anyway, in engineering, so for the rest of your life, because you were all engineers, in engineering, we use the letter J for the imaginary number. So you might as well get used to it because that's what we're going to be doing from now on. So the two roots are now going to have the form minus a over 2 plus or minus j, which was the square root of negative 1, times the square root of b minus a over 2 quantity squared. Basically, how I get this term is I take this 2 here, stick it back inside the radical as a 4. We can write the solution as a over 2, we're going to call a new variable alpha. We're going to call that the damping coefficient, also called an attenuation constant. The square root of b minus a over 2 squared, we're going to call omega d, we're going to call that the damped natural frequency. There's also another term called the natural frequency, which is omega naught, which is just the square root of b, or 1 over the square root of LC. And it turns out that omega d, omega naught, and alpha are related by this expression here. Don't worry about these details at this point. At this point, what you want to know is that in the underdamped solution, your characteristic polynomial will have two roots that are complex conjugates. So just in the overdamped case, there are going to be two candidate solutions to the differential equation. A1 times e to the s1t plus a2 e to the s2t. And as in the overdamped case, A1 and A2 will depend on initial conditions. We can actually simplify this expression using Euler's formula. So Euler's formula, and it is pronounced Euler, not Euler, Euler's formula basically says e to the j theta is cosine theta plus j sine theta. You might remember it as e to the ix is cosine x plus I sine x. It's the same equation. So doing some algebra, our solution is going to be a1 e to the s1t plus a2 e to the s2t. Remembering that e to the a plus b, you can rewrite as e to the a times e to the b. So this term and this term, we could rewrite as that and that. We can now factor out the e to the minus alpha t, and we can evoke Euler's formula to write x of t is e to the minus alpha t times what? Times A1 cosine omega dt plus j sine omega dt plus A2 times cosine negative omega dt plus j sine negative omega dt. But cosine of negative omega dt is just cosine omega dt. Sine of negative omega dt is just minus sine omega dt. So we get that. We can then combine this term and this term together, and this term and this term together to get this expression down here. It turns out that A1 and A2 are complex conjugates of each other when you solve for them. If you recall, complex conjugates means if one is something like 3 plus J4, the other one is going to be 3 minus J4. Turns out that if you add complex conjugates or subtract complex conjugates, you end up getting just a real number. So when it's all said and done, we get this final result here, which is the only thing on this page that you really need to worry about at this point. When you have an underdamped case where the radicand is negative, your solution x of t is going to be e to the minus alpha t times d1 cosine omega dt plus d2 sine omega dt. This is nothing more than decaying sinusoid. If you were to plot this, you would see that the response is going to look something like that. This is what we call our envelope decay. And it's going to depend on alpha. This is our actual decaying sinusoid, and its frequency depends on omega d. So what we're going to see is that the roots of the characteristic equation, S1, S2 equals minus alpha plus or minus j omega d. The alpha and the omega d both have physical significance. Alpha shows up here, how quickly the sinusoids decay. Omega d shows up in here, how quickly they oscillate. And you can think of this alpha once again, it's like 1 over a time constant. So let's look at this with some numbers. Suppose you have a characteristic polynomial s squared plus 0.02 times s plus 25 is equal to 0. So a is 0.02, b is 25. You get the roots. The roots are going to be minus 0.01 plus or minus J5. What we're going to see is that we have an oscillation of 5 radians per second and a decay of e to the minus 0.01 t, or e to the minus t over 100. In other words, this looks like a time constant of 100 seconds, which means it would take 500 seconds to go to 0. So this actually looks like it's not decreasing, but it actually is decreasing very, very slowly. If, on the other hand, suppose you have a characteristic polynomial, s squared plus s plus 25 is equal to 0. If you calculate those roots, these roots are negative 0.5 plus or minus j 4.9749. So the frequency of this decaying sinusoid is going to have a frequency of 4.9749 radians per second, almost the same as in the first case where it was 5. But now, if you look at this envelope decay, this is now e to the minus 0.5t, or e to the minus t over 2. So this has a time constant of 2 seconds, which means it only takes 10 seconds to get to 0. So here we see the decay much more readily than in the first case. You see that by the time you get to 5 seconds, it's actually down pretty low, and certainly by the time you get to 10 seconds, it would be gone. Look at this third example. If the characteristic polynomial is s squared plus 5s plus 25 is equal to 0. If you find their roots, those roots are going to be minus 2.5 plus or minus j 4.33. So now this exponential envelope is e to the minus 2.5t, or e to the minus t over 0.4. So this has a time constant of only 0.4 seconds. So by the time you get to 2 seconds, it's basically 0. You still have this oscillation inside with a frequency of 4.33 radians per second, but because the decay happens so quickly, you don't see much of the oscillation. So bottom line, in all three cases, we have this exponentially decaying envelope, which depends upon alpha, which is what? It is the real part of the root. Likewise, we see that the frequency of oscillation is dependent upon omega d, which is the imaginary part of the root. Bottom line, in an underdamped RLC circuit, we're going to get responses that are decaying sinusoids. I should point out that there is a special case, what we call lossless LC circuits, where no resistor is present. These are cases where the alpha term is actually 0. E to the 0 is just 1. Basically, no decay. We're going to call this the undamped as opposed to underdamped response. We'll talk about that later. This is going to give rise to an oscillator circuit. Okay, we're finally ready to briefly talk about the third of the three cases. These are critically damped. These are the cases where the radicand is 0 when a squared equals 4b. What we're going to see is now we have two identical roots. S1 and S2 are both going to be the same. It's going to be minus a over 2. Remember what a is. A is either R over L or 1 over RC, depending upon whether we have a series or parallel RLC circuit. Because these two roots are identical, at this point you have only one feasible solution. Let's call it B1 e to the st. But once again, if you remember from Math 250, in the critical damping case, you get a second solution of B2t e to the st. And so your total solution now is going to be some linear combination of some constant b1 e to the st plus b2 t e to the st. For example, it might be 5 e to the minus 4t plus 6t times e to the minus 4t would be a typical response. And these b1 and b2 coefficients will depend upon the initial conditions. We haven't gotten there yet. But bottom line is this is what we call the critically damped case. Okay, so let's sort of summarize our results. We saw that whether you have a series or parallel RLC circuit, and whether you're talking about the current through the inductor or the voltage across the capacitor, when you try to solve the circuit, you will get a second order constant coefficient differential equation, and it's always going to be of the form x double prime plus ax prime plus bx is equal to 0. The only difference is in that middle term, that a term. A is either r over L or 1 over RC. Here's a good mnemonic for trying to memorize which is which. So if you think about a series RLC circuit, the common variable is the current. Currents you associate with inductors. In a first order inductor RL circuit, the time constant is L over R. So this middle term is 1 over the time constant associated with an RL circuit. In the parallel case, the common variable is the voltage. You associate voltages with capacitors. In a first order case, a capacitive RC circuit has a time constant RC, and this middle term is 1 over that time constant. So I find these two mnemonics to be very useful in remembering what this term A is going to be. Notice B in both cases is 1 over LC. So A is a 1. They can take on two different forms. Then solving that characteristic polynomial, once again we have three cases: overdamped, underdamped, and critically damped. In the overdamped case, it just looks like two decaying exponentials. And the amount of decay is directly related to the two roots. In the underdamped case, we get a decaying sinusoid where the real part of the root dictates the envelope decay, and the imaginary part of the root dictates the frequency of oscillation. And in the third case, critical damping, we get this decay where you get b1 e to the st plus b2 t e to the st. Okay, this lecture was a lot of theory, not many examples at all. Next class, we will bring this all together with an algorithm and then lots of examples to show how this gets used. Have a good day.